Hello, everyone. Apologies for the delay. We had some technical issues that is now solved. Thank you, everyone online as well. So welcome to this ACAL seminar series. Today, we have a topic that actually mixes the two things that we have been treating the most recently, that is reasoning and planning with language, with Albert from Mistral AI. So the plan, for those of you who don't know how these seminars go, is usually 1 hour talk, questions. If you have doubts on the go, you can ask. If not, at the end, there will be time to ask further questions. And for those of you who are in person, there will be some time to network with the speaker or the organizers at the end with some food. The seminars are sponsored by DeepMind, InstaDeep, and Iconic. And we will have one more talk on foundational models for reinforcement learning for drug design on the 9th of July. And probably that will be the last one until after the summer. With all of this, now I give the stage to Albert to present his work. Thank you for coming, Albert.
Thank you so much. So hello, everyone. My name is Albert, and I'm an AI scientist working for Mistral AI. So Mistral AI is a French AI startup that just raised $1 billion, and we want to do good large language models. And I lead the reasoning team here at Mistral. And this is something that's super new and super exciting for me, because when I accepted the invitation to speak here, we didn't release the model yet. So I was really unsure of whether I can talk about this. I was having a really conservative title for everything, but now I'm really glad that we managed to release the model and the paper last week, so I can speak very freely. So what am I going to talk about? I'm going to talk about how to create reasoning models. So reasoning models, the earliest example might be OpenAI's O1 models and O3, O4 series, and also the R1 model from DeepSeek, which really started a really great example of both open sourcing the model weights, as well as open sourcing parts of the model training recipe, which we really want to echo with our project here. So I'm going to talk about a lot of details of how to train reasoning models that are based on large language models. There might be. Oh, okay, perfect. So I'm going to talk about a lot of details with respect to this. So the content of the talk will be how did we train Magistral? So Magistral is the name of the reasoning model. What did we learn? We have learned some really interesting stuff with respect to both the reasoning model itself, as well as multimodality, as well as how does the set of model weights actually move in the weight space. I think there's some super interesting stuff there. And also we're going to talk about some future directions, which will be the last part. So this is the tech report that we released. I highly recommend you to go and take a look. It's just called Magistral, and here I list my colleagues who are the core contributors in the reasoning team. So to begin with, I don't want to bore you with a really subpar reasoning model. So how good is it? We're comparing the Magistral medium model, which is a much smaller model than DeepSeek R1 and V3 series. But you can see we're on these major reasoning benchmarks, such as AIME, 2024, 2025, as well. So these are American Invitational Math Olympiad questions. So you get past this exam to actually represent the US in the IMO. And you also have the GPQA Diamond, which is like graduate level question answering. You have Live Code Bench and Aider Polyglot, which are more coding benchmarks to test the model's coding capabilities. So these are basically the core reasoning capabilities that we care about. Obviously, it's not going to be limited to just these capabilities, but I want to show you that we're very close to the DeepSeek R1 model from January. They massively improved the model, which kudos to them. But we are with a much smaller model. We managed to achieve quite similar performances. And if you take into account that sometimes you can do majority voting, we can actually do quite a bit better. Okay, so that is very vague, and we'll have the numbers, but what actually does the number mean? Here is a really popular video. You might have seen it on YouTube. On Twitter many times. So this is a test of that you pose to reasoning models, which is, can you create some JavaScript code or some HTML that animates a bouncing ball inside a rotating hexagon? So we did. So obviously, the first thing after we created model, we just put the models to test, and we managed to the model just one shot generated these JavaScript code which animates whatever all these bouncing balls inside, and you can see it's also affected by gravity. But we also wanted to ramp up the difficulty because we're really proud of this model. So we ramped up the difficulty, and here's what we asked. We asked for not just hexagons, not rotating hexagons, but rotating polygons, and the number of sides must increase for every single cell, and you have like different color balls of different colors, and that's rotating in different directions and in different speed as well. So just some really qualitative tests to show you how good we think the model. We think the model is quite good, and we managed to validate this with these qualitative examples. Okay, so how do we train it? We have two models. The first one called Magistral Medium. This is medium-sized model, much smaller than the DeepSeek R1, which is 670 billion parameters, although it's a mixture of expert models, so the active parameters is a bit lower. So we start from the Mistral Medium 3 instruct model. So instead of starting from a base pre-trained model, we start from an instruct model. But you'll see that actually these things don't really actually make that much difference. We did pure reinforcement learning on mathematical and coding questions. You can think of it as like basically putting you through like a 4-year pure math and coding curriculum. I don't know if anyone had that experience in their path before. And then we used Magistral Medium to generate responses on the open thoughts dataset. So open thoughts dataset is also a dataset of math and coding questions. And then we start from, and for the smaller version, which we open source, so this is Magistral Small, it's 24 billion parameter model. We start from the Mistral Small 3 instruct model, and we performed supervised fine-tuning on the open thoughts dataset, where the responses are generated by the Magistral Medium model. And then we did further RL on mathematical and coding problems. So this is the RL algorithm, and this is kernel's original recipe, GRPO, group relative policy optimization. And I got a show of hands, like who here know how PPO works? Okay, that's great. So I'll try to spend some time talking about PPO. So PPO is proximal policy optimization, which is a super old RL algorithm, which was first introduced by OpenAI in like 2017, 2018, when they were trying to play Dota, right? So it's a super old algorithm, but it seems to have stood the test of time. So what PPO does is that it assumes that when you're doing this reinforcement learning training, at every single step, it don't move away from the original policy too much. And then you can actually very nicely prove a mathematical lower bound that your policy is actually improving. So that's roughly how PPO works. There's a lot of mathematical details here, but I don't want to bore you with that. And the GRPO algorithm can be seen as a variant of the PPO algorithm, where instead of using a value model for guiding your policy, you actually use the advantage function, which is like for math and coding questions, is like, I have a math question, I generated an answer, did I get that right or not? Which is super simple, 1 or 0. Okay, so this is the algorithm that DeepSeek used to train their R1 model. We took that, we were inspired by that, but we did a lot of optimizations with respect to it. So here, the red bits are the things that we actually optimized. So you can see that we're mostly optimizing for efficiency here. So the first change is that we normalized the advantage function with respect to the number of tokens you have in a sequence, and we did some modifications with respect to the normalized advantage function and the clipping tolerances. So like these are the changes. You can read about them in detail in the paper, but I won't go into detail here because they're just simply too mathematical to cover here. Okay, so when you're doing reinforcement learning, obviously you need to have a reward. What exactly do we want to achieve here? So this is how we design the reinforcement learning algorithm. We want to design it from backwards. So we want to have a product that is a reason model that acts as a chatbot you can chat with. So what exactly do you look for in a chatbot and a reasoning chatbot, right? So there are a couple of things. So first of all, formats, we want to make sure that you can easily separate out which are the thinking bits and which are the actual answer bits. So we enforce the format to have just one set of HTML like think tags. So whatever is in between these thinking tags are considered as thoughts, and whatever is outside are the summaries. And then we use these like box formats for mathematics, and we use markdown blocks for code. For correctness, it's very simple. For math, we have a bespoke verifier with a combination of simple and different parsers to check whether the model generated answer is in line with the ground truth answer. So the reason why we have to use SimPy is that for mathematics, sometimes you come up with very complex expressions that's not just like an integer in the answer. You have to use some sort of bespoke checking to make sure that if you come up with an answer that's equivalent to the final answer, but not exactly the same, that you can still think of them as the same answer and give a good reward. So you don't want to penalize the student when they're actually doing something correct. And for coding, we have for each individual question, we have 20 unit tests that have time and memory limits, kind of similar to what you would do when you're on leak code or when on these like coding competition problems. You want to make sure that you can solve the problem, solve all the unit tests within a specified time and memory limits. For the generation length, you might have seen that for reason models, the generation length is usually super long. So we to prevent that from happening, we give the generation the soft penalty after it reaches a certain limit, so that the model learns, okay, I don't want to go near that. I want to be concise while still solving the problem. And then once the model generates generally super long sequences, we actually give it a hard penalty. So like there's no reward if you're just babbling and just generating too long sequences. The last bit, which I think we're particularly proud of, that is language consistency. So if you talk to some of the models today, for example, Gemini, you will realize if you ask a question in a different language other than English, whatever language you're using, the thinking process will always be English. So like if you ask a question in Korean, it won't generate Korean thoughts. So so the only thing you can see is that the summary is in Korean. But what if you suspect that the thinking process might be wrong? Then you go back to the thinking process, which is in English. What if you cannot speak English, right? So so this is something that we designed for, that we want the user to be able to check for both the thoughts and the final answer in the language of their choice. So we enforce this language consistency by giving the model an additional reward if the reasoning thoughts and the answers are in the same language as the user. And we only specify 6 languages, which are in addition to English. So we specify French, Italian, German, Spanish, Russian, and Chinese for these 6 languages, and you give it an additional reward if the answers are in the same language. And we put 10% of these multilingual data, and this seems to have worked. If you talk to our model today, it will be answering your question in whatever language you choose. So this is the exact form of the land penalty, but it's in a paper. So to give a multilingual example, remember we only use the major European languages plus Russian and Chinese. So I was trying to test it to the limit. So I was asking a question in Hungarian, and I'm not sure if you can see, but like all the thoughts and even searching the web, like it's using Hungarian, and also the generation answer is also in Hungarian. Any Hungarian speakers here? Yes. Yes. Go ahead.
I was just wondering if you also noticed that this actually increases the what is it just?
Oh, it's just for the consistency, but we find that these sort of things actually transfers. So if you can solve a math question in Russian, you can probably also solve it in English, because these the underlying reasoning circuits are kind of similar. You're just making sure that the model doesn't forget to answer in the same language as the user. So it doesn't hurt if you want to reason in English and then answer in Russian, but in the end, you want the user to be able to check your thoughts. Okay. Yeah, so I think this is a question about the Hungarian parliamentary elections. Then next, I want to talk about our large-scale distributed reinforcement learning pipeline. And this is something I'm super personally very excited about, because we spent really countless nights just building this pipeline. And I think we have like 10 really dedicated engineers working on this for a couple months, and then we have a reinforcement learning pipeline that we're actually very proud of. So to set things up, what exactly do you need in reinforcement learning when you're training language models to be reasoners? So you need three different kinds of things. So you need trainers. So these maintain the main copy of your model weights, as well as the optimization states, and calculate the gradients and perform the gradient updates. So typically you would implement this in PyTorch or JAX or TensorFlow for any likely users of that language. But I think reinforcement learning crowds are usually more likely to use JAX and PyTorch. For language models, you also need generators. And why is that? Because when you're using like a traditional reinforcement learning pipeline, you do some sort of target gains, and in that case, using PyTorch is fast enough, right? The rollout is not that slow. But when you're using language models, and these are really big monsters, like hundreds of billions of parameters, and if you just use PyTorch, it's not going to be fast enough, because you don't have the inference-aware kernel pipelines kernels that actually make your inference faster. And because we're training reasoning models, the generation length can be super long. So one single generation can be 32K tokens or 40K tokens. Like, think about that. So if you actually take if you actually can generate 40 tokens per sequence, it actually takes like 1,000 seconds to generate one single action, right? That's super long. And so you don't want to do that in PyTorch typically. And there are these really nice inference pipeline providers such as VLM and SGLang, which have inference-specific optimizations that make this process way faster than if you just do it in PyTorch or JAX.
Sorry, can I ask a question?
Yes.
I thought Mistral had a partnership with Rock, like the hardware provider.
Cerebras.
Yeah. So is this part of your system, like using accelerated hardware for language model?
It's in our inference pipeline, but not in the reinforcement learning generators. And I'll explain okay. The reason for that is when you're doing reinforcement learning and you want to stay as on policy as possible. So in that case, you need the trainers to always update the generators. And if you're using Cerebras, we're potentially talking about pushing some weights from GPUs to Cerebras hardware, which is tricky. So for that, you need something that's more integrated.
Yeah,
so we're
hardware compatibility.
Yes. So currently we're just using GPUs. So we're just not Cerebras. What Cerebras makes is like one giant CPU. We don't have that at the moment, so we don't use that for generators. I'll talk about that in a minute. Yeah. So that's something that you implement in VLM or SGLang. And also there's verifiers. So the verifiers are these like really beefy CPU nodes that actually verify whether the provided answer is correct or not. And sometimes they have to run really heavy computations using SymPy. And when you're doing coding things, you want to make sure you're executing the code in a safe environment. So you use E2E or model. So these are the kind of things you will implement the verifiers in. Okay. So there's a central tension, a very fundamental tension between generating, training, and verifying. And why is that? So when you're training language models and you're generating many sequences in parallel, the output sequences can differ a lot in their length, right? So the language, if you have enough diversity, in one sequence you might decide to stop after 2,000 tokens. In another sequence you might decide to stop at 32,000 tokens. So the distribution of the generation length differ really quite a lot, and it's very heavy-tailed. So if your generation speed is like 50 tokens per second, then the difference between your fastest generation and your slowest generation is going to be 7.5 minutes. which is really, really long. And if you want to wait for all the sequences to finish, then for these 7.5 minutes, a lot of your GPUs will be idle. And we never want GPUs to idle. We can rest, but the GPUs must stay training. So you don't want them to be idle for long periods of time. And also you need to update the generators with the new weights from the trainers, right? So how exactly do you work with this? Ideally, you want something that's as efficient as possible, but you also want to update the generators and actually make sure that the weights are, the generations are on policy. So here is our RL infrastructure in one picture. I'm going to talk in the POV of a data point, right? So you can see these things, these like sequences are the data points, and they go through the four stages. So first, they go through the generators. So the data points go through the generators and they get produced. You can see that they vary in length. They have very, very different length. And after the generation is finished, they go to the verifiers. The verifiers tell you, okay, you didn't correctly solve that math question, or you failed that code question, or you were correct in there. So the verifiers give you a 1 or 0, typically a 1 or 0 signal, and we identify that with the green dot for a correct signal and the red dot with a wrong signal. And then the data points, after being verified, will go to this will go to this batch. So this is what you want. So this is what you want to put in the trainers. So this is one batch of sequences. They vary a lot in length, but we can have a buffer that sort of nicely distribute such things. You put this batch into the trainers, and the trainers finish their updates. And after the trainers finish their updates, remember I said that we want to stay on policy. Staying on policy means that as soon as you finish doing one gradient update, or as soon as you finish one single batch, you want to update your generators with the trainer weights. And you just, in our pipeline, we just do that directly. So what do I mean by that? That means the generators are producing sequences, and on the fly, so it might be still generating like thousands of sequences. On the fly, we just change the weights, like just swap the weights. So what ends up happening is that a single sequence might be generated by 5 different sets of weights, right? So like you keep updating it, and if you have a super long sequence, like it might be generated by 5 different models. So I'm pretty proud of our infrastructure because it's as asynchronous as possible. We don't wait for anything, and the trainers and the generators just keep running. So that makes our training infrastructure really, really efficient. So there are asynchronous updates everywhere. So the generators never wait for long sequences to finish, and they should run at maximal throughput at all time. Trainers never wait for generators to finish generations before doing the weight updates. And also the trainers send the weight updates to the generators while they're producing sequences. And this is done via NICO. So NICO is GPU to GPU communication. You don't go through the CPU layer, because as soon as you go through the CPU layer, you turn the GPU weights, you push the GPU weights to the CPU memory, and you consolidate to disk, or maybe you don't, but that's going to take you a lot of time. And for example, if you have a 24B model, that's going to take you 3 minutes, and you don't want to wait for that. You want to basically just push the GPU weights directly from from one set of GPUs to another set of GPUs. Yeah, so that's our reinforcement learning pipeline, which I think is really, really quite efficient, and it really maximizes efficiency. And we find that it's a good trade-off. So you do lose a little bit of on policiness, because a single sequence can be generated by 5 different sets of weights, right? So you are a little bit off policy. But in our preliminary experiments, and we explain this in detail in our paper, that is actually fine. It doesn't hurt your performance if you're slightly off policy. So with that reinforcement learning pipeline, yes. So slightly. So usually when the way you measure off policiness is that you can take a look at the generated sequence, and then you take the old model, and you take the old model, and you take the new model, and you calculate the log probabilities over this sequence, and you can calculate the KL divergence. Well, you can have an estimator of the KL divergence. because if you calculate the full KL divergence, it's very expensive. But you can use an unbiased estimator for the KL divergence. So when you're doing asynchronous updates, your KL divergence between the new and old policy is larger than if you wait for everything to finish. But we find that that trade-off is actually very much worth it, because you are like, if you do everything synchronously, you can do like 100 steps, but if you do asynchronous, you can do 1,000 steps. So that's very much worth it. Okay, so with that reinforcement learning pipeline, we started training models. So we started with Mistral Medium 3. We performed pure RL from scratch. So there's absolutely no distillation from stronger reasoning models whatsoever. We just take the instruct model and we run with it, do the reinforcement learning. Yeah, so the performance of magistral medium. So here we basically it's the same table of results that we've seen from the first bar chart. And we plot we in this table we put down the performances of on these benchmarks, and we're trying to compare ourselves to DeepSeek R10. So this is a version of DeepSeek R1 that's also trained with pure reinforcement learning without any distillation on itself. And because we're also doing just pure reinforcement learning without distillation, we're trying to compare ourselves with that, but also put the DeepSeek R1 performances in. So to note, this is the DeepSeek R1 model from January. So when they actually first published the paper, obviously they've improved a lot. But this is, we're trying to compare with the model in their paper. So on the AIME 2024 and 2025 benchmarks, in addition to showing the passive 1 result, we also show the majority of 64 result. So what does majority of 64 mean? That means for the same question, you will try to generate, instead of just answering it once, you try to introduce a bit of diversity in your generations, and you generate 64 times. And then among these 64 answers, you're doing a majority voting of the answers, and you pick the one that has the most votes. It can be seen that in our model, we actually see that there's quite a bit of difference between the passive 1 result and the majority has 64 results, which has not been the case for most previous reasoning models, because what people usually report is that as soon as you start doing reinforcement learning, you're kind of making the distribution collapse. You're trading diversity for performance. So your majority of 64 result is actually very similar to your passive 1 result, because you're kind of collapsing the diverse distribution into a very narrow distribution. So, but we actually see that, for the magistral medium model, there's actually like 16 to 20% difference between the passive 1 and the majority of 64 results on AIME benchmarks. So that means either we're doing something very right or doing something very wrong. And that's something we really want to figure out. Okay. And then I'm going to talk just very briefly about reasoning reinforcement learning on top of cold starting models. And by that I mean the magistral small model. So the way it's trained is that after we train the magistral medium model, we used it to generate a lot of traces. And then we use those traces for the supervised fine tuning. And after the supervised fine tuning, we do exactly the same reinforcement learning that gave us magistral small. And here's the performance of magistral small. And you can see it's actually, so in the DeepSeek paper, again, they were saying that, for really small models, it really helps the model's performance if you do distillation from larger reasoning models. And reinforcement learning is not going to help you that much, at least not as much as the distillation. Here we're presenting a slightly different finding. That is, we performed three kinds of different things. We performed just pure supervised fine tuning. We did reinforcement learning from scratch without any distillation. We also did first supervised fine tuning plus RL. So you can see that if you read the scores, you can see that the performance of the reinforcement learning only model is not that much lower than the supervised fine tuning model. Or in some cases, for example, in the GPQA diamond benchmark, it's actually like 5% higher, which is quite significant. But what we're encouraged by is that we find that after you do the distillation, there's actually a way that you can improve the model by doing further reinforcement learning. So you can combine the two and actually make a much better model. So on the third column, you get the model that's first SFT and then RL. So this is the version that we released called Magistral Small. And you can see that it's actually basically like performing quite a bit better than the two previous models. Okay, here I want to present the list of findings that we think are quite exciting. So here is a very long-standing myth when you're doing language model training. That is, if you train on some mask data, then your coding performance will be better. If you train on some coding data, then your math performance is going to be better. I think kind of similar to how humans behave, I think. But this is just being a myth, I think, for a very, very long time. But there's never, you hear about it during Europe's, in the OpenAI after party that this is the case, but we never really confirmed it. But here we are, we're showing that if you're talking about reinforcement learning, then this is actually the case. So AIME and Live Code Bench are the two representative benchmarks that were selected to represent math and coding. And we have the starting checkpoint, which is really quite poor on both these benchmarks. And then we performed reinforcement learning on math only and code only, and see if they gain performances on the other benchmark. And you can see it's like gaining quite a bit of performance, right? So if you only do reinforcement learning on math, of course you're going to improve on your math exam performances, but you're also gaining like 15 to 16% on the live code, like coding performances. And if you're only doing coding, you can also gain like 17 to 18% on math, while also like getting a lot on the coding performances. So I think I have this confirmed for reinforcement learning. There's this debate about how large you should set your batch size and how large should you set your mini batch size in reinforcement learning. I recommend that you read this in detail in the paper, but the learning is that for simplicity, you can just set the batch size to be equal to the mini batch size, and you want to make it sufficiently large. And as long as it's sufficiently large, it doesn't make much of a difference, like how large you set it. So this is quite detailed, so I recommend to read the paper. This is something that we're really excited about. So after we trained the models, we performed some PCA analysis of the model weights. So this is on the 24 billion parameter model. So when you're doing PCA on 24 billion parameter model, you're really analyzing some vectors that live in R 24 billion. So like really, really huge vectors, very, very high dimensional vectors. We analyzed the entire training trajectory, and we find that there are two, and we've picked the top two principal components of the from the PCA analysis. And here in black, you can see these arrows. They go from here to here, and these represent our training trajectory. And then after we plotted the training trajectory, we did some perturbing of the model weights, and then we checked the model's reward on a given validation set, as well as the output length on a given validation set. And then we plot the gradients here. So you can see that these two principal components actually are quite meaningful, and the output length and the rewards are very highly correlated. So you can think of the process of doing reinforcement learning as increasing your reward and output length at the same time. It's unclear which one is the cause and which one is the consequence. But you can see that like they are actually very highly correlated. And when you're doing reinforcement learning, you are improving both reward and the output length. So I think this really helps us to understand how the model, the training dynamics when you're doing reinforcement learning. And we'll keep doing after the paper has been published, we'll keep doing science on this matter, and I think we have a much better understanding of the training dynamics than we were a week ago. So this, I think, is something that's going to be particularly exciting for the multimodal folks. So when we train our model, we talked to the product people, and they were like, "Oh, can we just train a text-only model with no vision capabilities?" And they were like, "Yeah, fine. Yeah, you can do that." So we just like, when we took the like the initial model, we just remove the vision encoder. So and just train on purely text data. So there's absolutely no multimodal data whatsoever during our training. And then after we train the model, for completeness, we just like reattach the vision encoder, but the vision encoder has never been trained during the RL process, and we just didn't expect it to work at all when there's vision data. Because why would it? Because when you're doing reinforcement learning, you change the weights a lot, so you must have messed up all the nice visual representations, or it won't be able to utilize nice visual representations from the vision encoder. But then we had an intern who came in, and they were like, "Oh, you have trained a reasoning model, right? Let me evaluate this on multimodal data." And then they realized, okay, this is pretty. You do some pretty nice vision-based reinforcement learning, right? Because it's gaining 5 to 6% on all the benchmarks I have, which is super exciting, super surprising and exciting for us because we never expected that this is going to happen. So on these 4 benchmarks, which are MMLU, MathVista, MMLU Pro, and MMLU Pro Vision, so these are the standard multimodal benchmark that we care about. We found that despite having seen absolutely no vision data during its reinforcement learning phase, it's actually gaining like sometimes 2%, sometimes as high as like 4 to 5% on these benchmarks. So it's worth noting that these are like quite academic type benchmarks. It's more like asking a question about physics, and so it's not like completely surprising that the reasoning model is going to do better at these things. But because these benchmarks really require the vision capabilities, which is because we expected the vision capabilities to be completely messed up. This to have any gain without any regression is already quite surprising. And there's a multimodal example. I'm not sure if it's large enough for you to see, but so here is a physics question about a light that enters into 2 different media, and from medium 1 to medium 2, 3, to medium 2 to medium 3, as shown in the diagram. So you have to see the diagram to actually figure out what is exactly what are exactly the mediums and what are the angles perspectives in this. And the question asked is like, what may be concluded about the speed of light in each medium? So this requires a little bit of physics knowledge, but it also requires you to read the plot properly. So our model before the reinforcement learning training was not able to do this, but after the reinforcement learning training, you can see that in the model generation, it starts by thinking. So it actually starts thinking about, okay, I need to understand the behavior of lights in different media, and what does the refraction mean what does the angle and the refraction constant? I think that's the word. What are their relationships? And then it concludes that, okay, the correct relationship is V3 is bigger than V1 is bigger than V2, which is the correct answer. And if you look at the thoughts here, it's actually also completely coherent. So which is also surprising because like we thought, okay, we really didn't expect vision to work at all. Yeah, and so that's a lot of like interesting findings that we wanted to share. But we also wanted to share like how do you we train this model, and it's not state of the art. It's still quite a bit away from state of the art. And by state of the art, I meant R1. So we know that if you do a bit of distillation and then do reinforcement, this works. We don't want to distill from larger reasoning models because we really avoid them like the plague. We just wanted to make sure that we have the recipe and the data to train our own reasoning model. But just as a validation, if we take the recipe, can we actually reach state of the art? And the answer is yes. So if you want to train the best model in class, so first you train the largest and best model possible, and distill that into your model. And the Mistral medium pure reinforcement model, that practice was just the aim is really for the reasoning team to learn stuff. But if you want to reach state of the art, we just did a small fine tuning of Mistral medium 3 on the DeepSeek R1 traces, and then we did reinforcement learning on top. And you can see that we're matching or even better than their performances. But this model is not released because we're really ashamed of any distillation whatsoever. We want to do our own models. And after publishing the model and the paper, we find that there are a lot of really very wide open research questions. For example, how do you do supervised fine-tuning and reinforcement learning on different data? How do you do this? And if you do this on different data, how does it actually change the model weights? So there's a lot of things with regard to the training dynamics that can be investigated. What data are the most generalizable? So if you just train on one specific kind of data, does that make your model a math junkie or a coding junkie? And it fails to generalize to outside of these domains. What are the data that's actually good for the model, right? And also there are like questions about, can we use formally verifiable rewards as in reinforcement learning playground? I did my PhD AI for formal math, so this is something that's super close to my heart. And I know at Imperial there's a cult around Kevin Buzzard, who's a formal math guy. So I think this is something that we're also very keen to play around with. And also, I think this is also just for the sake of science. When you're doing this kind of reasoning model training, what is the smallest experiment that you can run in terms of model size, data size, and the metrics? And what metrics do you actually monitor that still has an acceptable signal to noise ratio? So you want to figure out the smallest, cheapest training config that still tells you something about the science behind it. So what is the smallest experiment that allows you to do that? So these are like all very open research questions, and we really hope to tackle all of them. And we hope like some of us will be interested in joining us to tackle these research questions. So on the left is the QR code that has a referral link, and or you can just send me an email. It's aj@mistral.ai. We're taking full-time employees and also interns who are at the last year of their studies. So yeah, I think that's the end of my talk. Thanks very much.
So we have maybe a few questions online. Guys, this side, anybody wants to put this motivation?
Hi, thank you for a very interesting talk. I have a couple of questions. First question is about what are your thoughts on the balance between memorization and genuinely reasoning capabilities behind these reasoning models? Because we have these hot debates. Like, this is all memorization. No, this is not memorization. So what do you think? If it's combination of both, or probably like one component is more and another is less? And the second question related to that, you have this table 5 where you showed that you have some like knowledge transfer from code to maths and from maths to code. But what are, like, from your experience working with these type of models, constrained on this knowledge transfer? I give you an example. We have a benchmark where we have like a very simple facts, like Mary went to the bathroom, Mary pick up football there, Mary went to the kitchen. Where is the football? So it's like you need 3 facts to answer this question, and probably you have about 100 other destructive facts like this, like John went to the office. And what we see that all the state-of-the-art models like Gemini Pro 2.5, if you have 100 facts and your question requires only 1 fact, it gives you 100% accuracy answer. If you need to combine 2 facts in the same settings, it gives you 85% accuracy. If you need to combine 3 facts, you have 50% accuracy, which means that, of course, like Gemini Pro 2.5 trained on all this math, it shows an AI ME benchmarks like 70%, I don't know, 70%, but then it should like have 100% combined 3 facts to answer the question, simple, logical, like state tracking stuff. We have 50% accuracy. Certainly, if we will fine-tune on this task, we will get 100%. But so the question is how we can transfer from maths and coding to common sense reasoning. What are the constraints? How we should train these models, and balance between memorization.
Thanks for the 2 questions. I'll try to stay closer to the. I think for the first question, I don't know how to define reasoning. So usually when I talk, and so I get to debate this a lot with my friends, and usually the debate goes like this. They were like, okay, what is reasoning? What is memorization? I was like, oh, define reasoning. And they were like, hey, they define reasoning. So I was like, this is ambiguous, define that. And we go down this rabbit hole, and we just like, it's kind of similar to like the, define a chair. Right? After you define a chair, I'm going to ask you, is a camel a chair? And you'll find, okay, some of your, in your definition, you might not count as chair, but you might have not thought of that. So my personal stance is that we don't have a clear definition of what is reasoning, what is memorization. For most tasks, there's likely a combination of the two. And it's really hard to find a pure reasoning task or a pure memorization task that makes it easy to do scientific experiments on top of it. So I think that's like the state of the research on this direction. I don't have a solution. And on the second thing, I think for any agent, there's a power law relationship with respect to how many errors they make. So if something requires an hour to complete, and this model has a 5% chance of making an error, then you will find the error will accumulate. So if you have a task that requires 10 hours to complete, then you will have the chance of success is only 95% in the time. So if you need to combine multiple components, if it's not perfect, if it's not 100%, the performance is going to degrade, which I think is natural because we haven't trained the models on these kind of tasks, and we're expecting them to generalize out of distribution on these things like this in zero shot. So I think that's always going to happen if you don't fine tune, if you are doing out of distribution tasks. The question is really either you can verify the outputs, or how much tolerance do you give it? How error tolerant are you? And you can probably scope like how long the horizon you should give to your model. I'm not sure if that answered the second question, but I don't have better conclusive answers to that. Some questions?
Yeah. What are your plans on expanding? Like, you cannot like provide a good definition of reasoning, right? So, like, you're clearly aware that like adding more verifiers, more tasks, more data will expand the domain. So, if there's no ability to create anything that can generalize outside of it, I guess the next logical step is increasing the domain until nothing left. Well, until the money ran out. But like, what are the next one? What are the top 5 next reasoning-like areas that you're thinking might be cost and scale efficient to generate data for? Maybe like with formal verifiers, maybe like for semi-tuning something. Like, what do you think?
I mean, obviously I have a huge personal bias towards formally verifiable environments, but also I think things that, for example, making use of tools. So not just using pure text, but sometimes I can write some code to solve some question. Sometimes I can perform a web search. Sometimes I can perform all kinds of tool calls. To be able to learn to use these tools, I think will be a very good way to improve the reasoning performance. And I think to come back to the fact that why does math actually improve code? Why does code improve math? I think there's some underlying reasoning circuit below both tasks. And when you train on one, you improve on the other because you train the underlying reasoning circuit. I think these tasks, in my mind, doing formal verification plus using tool calls will also train the underlying reasoning circuit. It's not absolute because I cannot define reasoning, but I have a sense of what sort of tasks requires reasoning, and these are the things I see.
Small addendum. So thank you for the answer. But like, University of Edinburgh, like actually like really old institution with like a lot of AI stuff that started in the 60s.
Yeah.
So they have like AI, good old fashioned AI programs for 60 years. And they have like some definitions of reasoning, and maybe like Marvin Minsky definition to be like finding a path, like it's a loose definition of a problem, and finding a solution in this kind of like space, like semi-defined space of possible answers, right?
Yes.
So it's kind of a little bit like search.
Yeah.
But the generation is not search.
Yes. I'm really happy that you asked this question because I think some of the stuff that people did in Edinburgh actually like fed back to some of the formal verifiable environments research. Like people were starting with like SAT solving, that's the earliest theorem prover you can have, but then it gradually evolved into like simple type theory, which is equivalent to higher order logic, and then dependent type theory, blah blah, and then you have like these formally verifiable environments always implement some kind of logic, and very much underneath they are doing some sort of search. But the other point I wanted to say was that like we are not trying to solve an NP complete problem such as SAT solving, like solving arbitrary sets. Because like if you think about it, searching is a really hard problem, but humans seem to be really good at finding like 600-page long mathematical proofs. How did humans do that? Humans obviously didn't just search over the entire space for that, right? So that probably means that the mathematical questions that you're interested in are not arbitrary. They are interesting to some human definitions, probably easy to search for. So I think if we're taking very human-centric perspective, we probably just want to focus on that part instead of solving the general question of sets, like solving sets.
By search, I didn't mean like for loops, like 25 billion for loops. I mean like a star, a combination of traversal with heuristics and what else. But yeah, thank you for expanding on that. It's actually more interesting to hear not how your experience in like theorem proving and like math actually informs this. It was really fascinating. Thank you.
Thanks. So there,
if there's still time for questions. The one interesting thought about the movement of the weights, the comparison. I mean, the accuracy plot actually showed a decrease if you keep moving, whereas the output length would keep increasing. So is your generalization like the majority at 64 due to like, I mean, you said it's an open question to you guys, but do you have any hypotheses on why that is happening? Is that maybe a reason?
So I wouldn't extrapolate from that graph, because that graph was based on a PCA analysis of the existing weights. So the principal components are taken from the existing weights. So if you extrapolate from that, it's possible that it will become inaccurate, because like you might just move not in the, so if you move your weights not in the like extrapolating direction, but in sort of inside like the little sync direction, then you might end up with a different set of weights that give you a different set of principal components that improve on output, reward, and generation rate. But that being said, it's a very open question. I don't have the answer. We're actually looking at it. So one of the things we found was that it's actually the reinforcement learning algorithm doesn't change the weights that much. Change it very subtly. So that might be one really interesting thing to look into. Like compared to SFT, it changes very little. And there might be some interesting mechanism that's happening, like searching for a very intricate structure in the weight space. So that's kind of the ongoing research direction.
Thank you. Okay, so we're out of time. So if there are any questions left, remember we have the time now for the one per person. So let's wrap it up. Yeah, thank you. Our was super interesting. And hope to see you all of us a few days from this time. Remember we have another talk on the 9th of July. Thank you for coming.